Hello friends, in this video we are going to see characteristic of common emitter configuration of transistor. We have seen that because of high current gain and high voltage gain, common emitter configuration is used frequently. So here important parameters are, we have to study characteristic of common emitter configuration of a transistor. First we will see an experimental setup to obtain characteristic of common emitter configuration. So here we have shown some voltage sources, namely VBB and VCC, and this is a BJT NPN transistor, this is collector, emitter and base, and some meters are placed to measure some voltages and current. So what voltage we are going to measure? We are going to measure a voltage, that is VBE, between base emitter. We are going to measure a current, that is the input current, which is base current. Next we are going to measure the output voltage, that is VCE, and we are going to measure output current, that is IC. So this is an experimental setup for plotting characteristic of C configuration. I list out the input voltage, input current first. So input current is IB, that is base current. Input voltage will be VBE, that means voltage between base emitter junction. We have output part. In output we have output current as collector current, and output voltage will be VCE, collector emitter voltage. We have two parts of a characteristic. One is the input characteristic and second is output characteristic. So let's study first input characteristic. Now input characteristic is nothing but a graph of input current versus input voltage. So we have independent variable as input voltage. Based on input voltage value we will get input current. In this case input voltage is VB and input current is IB. So basically we have to plot a graph of VB and IB. So base emitter, if you see, it will be a simple PN junction diode. So the characteristic of common emitter configuration as far as input is concerned, will be just like that of a diode. But this will be true for a constant value of collector emitter voltage, because that should not affect the characteristic. So, this is a simple characteristic same as a PN junction diode. So, as I said earlier, here I am going to consider that this characteristic it holds true for one particular value of VCE. Now, suppose I increase the value of VCE, the characteristic will be same, but it will be shifted like this. So, this characteristic is for second value of VCE, and this case this VCE2 is greater than VCE1. Now, from this what we can get? We can get a parameter which we call as input resistance. Now, the parameters that we obtain from here is input resistance. Denoted as Ri. It is the ratio of change in the input voltage to change in input current at constant VCE. So, I will consider this graph and I will denote 2 points. This will give me one particular value of VBE and corresponding value of IB. And same characteristic, I will have one more point having the voltage VBE2 and corresponding current as IB2. So, I am getting here change in the input current, that I will denote it as delta IB, and corresponding change in the input voltage will be delta VBE. So, ratio of change in the input voltage to change in input current for constant VCE is nothing but input resistance. So, this value of input resistance is of the order of few hundreds ohm. So, here we have seen a input characteristic of a transistor resembles VI characteristic of a PN junction diode. Let us move to the next part, that is output characteristic. Now, the output characteristic is nothing but a graph of output current versus output voltage. So, independent variable is output voltage, and based on output voltage I will get output current. So, in this case output voltage is VCE and output current is IC. Here we need to pay attention because it is very important. So, the characteristic that I will get is like this. For one particular value of a base current IB. So, I will denote this as some value of IB. Let us take this as a 10 microampere and consider the very high value of a beta. I will consider IC as 1 milliampere. So, what happened exactly? So, for a small value of a VC, I will have a linear relationship between IC and VC, but beyond that I am getting IC nearly constant, which is independent of VC. So the voltage up to which I am getting a linear relationship between IC and VC, we call that as knee voltage. Normally of the order of 1 volt. Now let's have a different values of IB. So I will get a characteristic like this. And keep on increasing the value of IB, make it 20, then 30, 40, and corresponding value of IC based upon the value of beta, I will get here 2 milliampere, 3 milliampere, 4 milliampere. I can have a very less value of IB, so I will denote a hypothetical value or a characteristic for IB equal to 0 like this, because this is required for further analysis. So output characteristic has 3 parts in it. First part is below IB equal to 0. So denote it like this. We call this region as cutoff region. Then second region is this. We consider this region as saturation region. Between cutoff and saturation we have active region. Let's discuss one by one. What are these regions all about? So first is cutoff. If you see the characteristic properly, you will come to know if I have IB equal to 0 microampere, that means IC will also be 0. So when input current and output current both are 0, then that condition is a cutoff. So to get this, I should have IB equal to 0 and hence IC should also be equal to 0. So from both the regions I should have a 0 current. That is possible only when both the junctions are reverse bias. So when transistor operate in this region, then we consider transistor as an open switch because it is not allowing passage of a current. Let's go to next region, that is active region. So what happened? Now in active region, if I want a transistor should operate in an active region, then base emitter junction should be forward bias, and collector base junction should be reverse bias. Now let's see a characteristic once again. So this region is active region. So if you see properly what is happening over here, based upon the value of IB, IC value is keep on changing, but IC value is remaining almost constant for change in the VC. So what observations I can draw from this is IC increases slightly with increase in VC, but IC largely depends upon IB. Meaning, for a constant value of a VCE, if you increase the IB, IC value is increasing, and that proportion is this. IC will increase beta times IB. So remember, this relationship is true only in active region. So this relationship holds true only in active region. So what is happening over here? ICs keep on increasing based upon the value of IB. So transistor act as a amplifier in active region. Let's go to the third region, that is saturation. Now, for transistor to act as a saturation region, I should have both the junctions forward bias. When collector base junction will be forward bias? When I have voltage VCE, that means voltage between collector and emitter nearly equal to 0 or practically 0.2 volt, which we consider or call as VCE sat or saturation. So what I should have? VC value, if I am having 0.2 practically or 0 volt, then I can get VCB nearly equal to 0.7, and diode that got formed because of base collector junction will be forward bias. So here we are not going to make collector base junction forward bias by using a supply, but by having the VCE nearly equal to 0 or equal to VCE saturation, that is 0.2, automatically collector base will become forward bias. So what happens in a saturation region? In saturation region, current keep on increasing with the value of VC. That means it will allow a maximum collector current to pass through a transistor in saturation region. Now what happens in the saturation region? Collector current increases more rapidly with increase in VC. So that is an important statement in a saturation region. Collector current increases rapidly with increase in VCE. So transistor allows maximum collector current, hence transistor act as closed switch. In saturation region. What are the parameters that we can obtain from the output characteristic? Is nothing but output resistance. Denoted as RO. RO is nothing but a dynamic output resistance and defined as the change in output voltage with a change in output current for constant value of base current. So we can show that in the characteristic. So here let's check. This is the one point that we trace, and this is the another point. So this value is say IC1, and here this value is IC2. So there is a slight increase in IC for corresponding change in VCE. So the ratio of delta VCE and delta IC for constant IB is nothing but output resistance, which we call as dynamic output resistance of a transistor. Thank you.